Okay, what we're going to look at next is we're going to analyze a couple of functions that have a degree on the top higher than the degree on the bottom. Okay, we already know that from our earlier analysis that we're not going to have a horizontal asymptote in this case. Okay, we might have a vertical asymptote here depending on whether or not this factors and whether or not the bottom would cancel out. Okay, so we can test that if we'd like right away and see if this factors. We'll go x and x and then factors of 3. Okay, that would give us a sum of -2. Does not factor ultimately. So if this does not factor, then obviously that's not going to get crossed out. So we would have a vertical asymptote then at x equals -2. Okay. And so if we were going to go about to start drawing the graph of this, we could go ahead and plug that asymptote into our picture right there. And we discussed earlier that there's no horizontal asymptote because the degree is higher than the bottom. The top degree is higher than the bottom degree. And so what we're going to look at then is what does it behave like then at infinity? Because what we had looked at earlier in our set of rules was that there is no horizontal asymptote, but this is going to behave like the quotient when we actually do the division. Okay, and so let's see what that looks like. If I did x plus 2, and I did x squared minus 2x plus 3, and I did my long division here, I would get an x, be x squared plus 2x. If I subtract, I'm going to get -4x plus 3. X into that would be -4. And then it would be -8. I distribute 2x, or excuse me, -4 times each of these. And then if I subtract, I'm going to get -3, and I wind up with an 11. Okay. So in mixed number form then, again, this being essentially kind of like improper fraction form. Okay, in mixed number form, my same equation would be x minus 4 plus 11 over x plus 2. Okay. Now, here's the deal. This function, just like before, like we talked about, this is going to behave exactly the same way as our original function. Okay, it's just written in a different form. This is written in improper fraction form, if you will. This is written in mixed number form, if you will. Now, think about why these two behave the same at infinity. If you look at 11 over x plus 2, what's this going to be at infinity? If I put a huge number in there, it's going to be 11 divided by a huge number, which is essentially what? Degree on top is smaller than the degree on the bottom. This is going to go to what? It's going to go to 0. Okay, so at infinity, this is really just 0, isn't it? Okay, so is it surprising then that these two behave, that this one is going to behave like the quotient at infinity? Okay, it's going to behave like the quotient at infinity because that part of it is really just 0. So it's going to behave like this. It's going to behave like x minus 4. Now, similarly to what we did earlier when we had a horizontal asymptote, okay, that means that if this function behaves like this quotient right here, okay, that right there is a line, isn't it? It's not a horizontal line, but it's still a line. Okay, and if we were able to graph it, which we certainly can, it's going to have a slope of 1 and a y-intercept of -4. Okay, that line that we graph right there, okay, is also an asymptote for this function. Okay, however, it's not a horizontal asymptote. It's not a vertical asymptote. Okay, it's a slant asymptote. Okay, or we call it also an oblique asymptote. Okay, so now if we were to set out to graph this, okay, we would want to again pick points that are on either side of the vertical asymptote, and we should be able to plot enough points to see what this thing looks like. Okay, now let's go ahead and take a look at the graph of this and see if we get what we expect. On the top, again, we have x squared minus 2x plus 3, and x plus 2 on the bottom. And when we graph it, we can see that. Okay, keep in mind that this intersection between these two is kind of down far. We might not be able to see it here, but we know we should expect something on either side of the asymptote here, so I'm going to change my window to go down to -20, let's say. Let's see if we can see the other branch of this. Okay. All right, there it is. Okay. And then the other part to this is to just to illustrate. Okay, does it in fact behave like that x minus 4 asymptote? I'm going to go ahead and put that in there, x minus 4. And as you can see, what does that curve do? It gets closer and closer to that line, doesn't it? Okay. Because at infinity, as we go off to the right and as we go off to the left, okay, our conjecture was this function is going to behave like this quotient. Okay, and isn't it doing exactly that? Question so far? All right, let's look at another. This is number 47 from your book. This one is x cubed minus x squared plus 1 over x plus 2. So this time our function is cubic on top, linear on the bottom. Okay. And based on our previous work, what would we expect here in terms of the behavior at infinity? Okay, we know the top is bigger than the bottom, so there's no horizontal asymptote. Okay, last time when we did the division, we wound up with something linear. Okay, what are we going to wind up with if we do the division this time? Something what? It's going to be something quadratic, isn't it? So does that mean that we're going to have like a slant parabola, if you will, or an oblique parabola? Okay, essentially, but those aren't really the words that we use for this. Okay, ultimately, this is going to behave like a quadratic equation, so that means at infinity, it's going to have a parabola shape. Okay. And that parabola is going to be the quotient that we get when we do this. So we would still have the asymptote at -2, just like we had in the previous problem. Okay, but then we're also going to have essentially, okay, a model parabola. Okay, that's going to show us the behavior of this at infinity. So if we do this division here, x plus 2, x cubed minus x squared plus 1, and just for argument's sake, I'm going to do this with synthetic division just to show that we can. Because we have a linear divisor here, remember? So if we were to just do the synthetic division, 1, -1, 0, and 1. Okay. And okay. So if we were to bring down our 1, multiply and add, multiply and add, multiply and add, we'd get that. So our conjecture is that this function is going to behave like x squared minus 3x plus 6. Again, plus -11 over x plus 2. But remember, at infinity, okay, this is really a 0. Okay, if we put something extremely large in this, it's really just 0. So that means it's going to behave like this quadratic. Okay. Now, do we actually have to graph this quadratic on here to see the behavior? Okay, generally we wouldn't. Okay, we would at this point we'd just plot some points here on either side to get that graph. Okay, generally this problem would more than likely be on the calculator part also, so that we wouldn't have to do all that. So let's graph it and see if we get what we expected. So x cubed minus x squared plus 1 over x plus 2. I'm going to dump the oblique asymptote here. I'll draw on the quadratic in a minute. But let's take a look at the behavior of this. I'm just going to go zoom 6 and see what we see here. Okay. Alright, so we do get our asymptote here. It looks like we don't see anything on the left-hand side because it's probably either too high up or too high down for us to see it, or too low down, I should say. If we change our window, let's go, let's say -20 to 20. Maybe we'll see something on the left side of the asymptote. Still don't see it. Ultimately, we can look at a table as well and see what where we should be with notice that -6, we're already at -3, we're down to -35, or we're up at positive 35, so it's actually up, not down in this case. And you can see that there are big numbers over here. And I guess really, should that be surprising, knowing that it's going to behave like this? Okay, shouldn't both of them be up as we go to the left and right, since it behaves like a parabola? Okay, so another reason to know that. So if we change our window to, let's say, 50 this time, okay, there's the other part. Again, asymptote here, behavior here. And with that said, if we go ahead and graph that parabola that we think this ought to behave like, we should be able to see that as well. So if we do x squared minus 3x plus 6, along with our current graph, okay, notice that this one on the right, it mirrors it exactly, doesn't it? Okay. It's almost that parabola when it's even this far to the right. And this one, it looks like it's going to do exactly the same thing there. Okay. All right, so again, it's going to behave like this parabola. Now, we had a nice name for a linear situation when it was 1 degree higher on the top than it is on the bottom. We're always going to get a linear quotient, which means it's going to be a slant asymptote or an oblique asymptote. When it's 2 degrees higher, or 3 degrees higher, or 4 degrees higher, we don't really have a special name for this particular quotient. Okay, we just need to know that our function is going to behave like this quotient. Fair enough? Okay. Questions so far?